Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the primary and secondary bonding. So what is the importance of this primary bonding as well as secondary bonding? So generally, in order to describe any material or if you want to characterize any material, these bondings are very important. Why? Because the properties of the material or the characteristics of the material depends upon the type of bonding which the material has. So if there is a small change in the interatomic bonding between the atoms inside of the material, there is a huge variation in the properties of the material, whether it is a mechanical property, chemical property, or a physical property. So that's why the bonding energies are very important while selecting any material. So in any mechanical application or any engineering application, the selection of material depends purely upon the type of bonding which has. Suppose if I want to manufacture a good hard material, so this hard material, how you will select? Depending upon the type of bonding. So this bonding will give us the characteristics of any type of material. Now in this types of bonding, we have the two different types of bonding, that is the primary bonding as well as the secondary bonding. In the primary bonding, we have again three different types, that is the ionic bonding, covalent bonding, and the metallic bonding. And the second category is the secondary type of bonding. So we'll see all these types of different bondings in the materials engineering, and what is the importance of these bonding energies depending upon the type of bonding, how the material is being varying. Now this thing in the interatomic bonding, why we are studying means an important reason to have an understanding of interatomic bonding in the solids is to describe the type of bonding, and this allow us to explain the material properties. So mainly if you want to know the different properties of the material, we have to know what type of bonding the metal exists. And we have three different types of primary bondings or the chemical bondings which are found in the solids. Those are the ionic bond, covalent bond, as well as the metallic bond. And these three types, what is happening in this, for each type of bonding, it necessarily involves the valence electron. So in any type of these three, it should have an valence electron. So what is a valence electron means? It is the electron which is having on the outermost shell of the element, and this will transfer to another atom, another element, so that you can have a bonding between these two. So that's why we should have an necessary thing is what? It should have an valence electron of any of the three types of bonding. Further, the nature of bond depends upon the electronic structure of the constituent atoms. And also, though we are having a valence electron, the necessary thing, and also one more thing is what? The atomic structure, how the atomic structure is arranged, that is also important in the case of this type of interatomic bonding to describe any material properties. Now, in general, each of these three types of bonding arises from the tendency of the electron to assume the stable structure like those of inert gases by completely filling the outermost shell. So, what are the assumptions we need to take into consideration while we take this type of these three types of bonding? The assumptions are that the tendency of the atom to assume to be stable, and also the structure, the electronic structure should be like those of the inert gases, and it has to completely fill the outermost shell of the electron. So that is the three things we need to take into consideration while we are selecting any type of bonding in the materials. And the secondary or physical forces and engineers are also found in many solid materials, and these are very weak when you compare with the primary bondings. So most of the materials will have the primary type of bonding, but some cases we can find the secondary type of bonding also, and this secondary type of bonding will have a weaker bonding energy when you compare with the primary bonding. So that's why while selecting the material, we need to select a material which is having a good bonding energy. That means any of the three types of bonding, that is the covalent bond, ionic bond, or metallic bond. So from these three we have to select. Why? Because the bonding energy is very high when you compare with the secondary bonding. So the selection of material depends upon the type of bonding, because the bonding energy varies with the primary as well as the secondary type of bondings. And we'll see how the type of bondings will be there for each type of things. The first one in the primary atomic bonding is the ionic bonding. So ionic bonding. So what is the meaning of this ionic bonding? So there is a strong attractive force should be there between the atoms. So how we can generate this strong force of attraction means by the arrangement of the atoms inside the structure, that is the atomic structure of the material. So how we have to design in order to get the strong bonding, we'll see now. So in this ionic bonding, it is always found in compounds that are composed of both metallic and non-metallic elements. So where we can find this type of ionic bonding means where the metallic and non-metallic compounds are existing. In this type of things, we can find the type of ionic bond, and this we can easily find out from the extremities, right extremities of the horizontal in this periodic table. And atoms of metallic element easily give up their valence electrons to the non-metallic atoms. So what are the things we are seeing? That is the compounds which are existing between the metallic as well as non-metallic are called the ionic compounds, that is the ionic bonding, and these things will share the electrons. That's why whatever the metals, whatever the electrons are there at the outer shell of the metals, this will easily share to the outer shell of the non-metallic elements. Because of this sharing of the electrons between the metallic and non-metallic, we'll get a strong attractive force between them, so that there is a good bonding between the materials. And in this process, what is happening? All the atoms acquire stable or inert gas configuration because of the arrangement of the electric charge, and as they become the ions. So because of the arrangement of the positive and negative charges, they'll have a strong bonding energy between the atoms, so that you'll get a stable inert gas configuration things. And sodium chloride is the best example for the ionic bonding. So this is the classic example where the sodium as well as the chloride atoms will get a good bonding because of the arrangement of the alternative arrangement of the positive and negative charges between the atoms, so that you'll get a strong attractive force between these. A sodium atom can assume this electron structure of neon by transferring its one of the valence electrons to the chlorine. So the valence electrons, the outer shell of the chlorine is giving to the nitrogen neon, so that you'll get a positive energy and a strong attractive force between them. Now after such transfer, the chlorine ion has a negative charge and the electron configuration identical to that of argon. So what is happening here? Because of that sharing of electrons, the sharing of electrons, when it is sharing, it has a positive, and the element which is taking the atom which has having a negative. So what is happening there? There is a balance between the sharing and accepting of the electrons. So positive and negative. So because of this change of the charges, there is a strong attractive force between them. So because of that attractive bonding forces or Coulombic, that is a positive and negative ions, by virtue of the net electrical charge, attract one another. So as we know that dislike poles attract and like poles repel each other. So because of the attractive force, the bonding energy is very, very high. You'll get a solid material. Why we are getting the solid material means because there is a strong attractive force between the molecules inside. So because of that strong attractive force, we'll get a strong material. So in such a way that the bonding energy is very, very important while selecting any material. So this is how you have to arrange the atomic structure. So this is an example for the sodium chloride. If you see here, the sodium has a positive charge and the chlorine has a negative charge. So because of this positive and negative, what is happening? There is a strong force of attraction between these two elements. So anywhere if you see here, anywhere positive, negative. So if you see in this direction or in this direction or in this direction or in this direction, any direction if you see, always the charges should be arranged in such a way that a positive and negative. Like this, you have to arrange alternatively so that the complete set of the atomic structure should be arranged in a positive and negative alternative charges, so that there is a strong attractive force between these two, so that you will get a strong bond. So this type of sharing of electrons on the outermost shell of the two elements which is having a positive as well as the negative charges will have a strong bond or strong force of attraction. So this type of bonding is called as an ionic bonding. And coming to the second type of primary bonding, that is the covalent bond. Covalent bond is nothing but the sharing of electrons. So in covalent bonding, stable electronic configuration are assumed by sharing of electrons between the two adjacent atoms. So if you have two adjacent atoms which are side by side, so here there is a chance of sharing of electrons. So that is the thing in the covalency nature. Okay, when coming to the ionic bond, what is happening? There is a difference in charges. Because of the difference in charges, there is a attractive force. But in the covalent nature, you have the share of electrons. So in that way, you will share electrons from one material to other material, so that you will have a good bonding energy. So two atoms that are covalently bonded will each contribute at least one electronic bond. So how you are getting this sharing of electrons means, suppose if I have two materials which is having, this is the valence electrons. So when you can share means this electron will share with this. So sharing means from both the ends it has to share. So when you're sharing from this to this and from here to here also, it has to be also shared. So that's why there is a strong bonding again between these two materials. So sharing of electrons will exist when from both the ends, both the atoms should share, so that you will get a covalency nature. So here from A is sharing as well as B is also sharing. So since A and B are sharing each other, will have a covalence bond. So we'll see how the covalency nature will exist with the help of the methane. So what is happening here? The carbon has 4 valence electrons. So whatever the carbon is having, so this is the carbon atom which is having 4 electrons in the outermost shell. So initially the carbon is having 4 valence electrons. So from these 4 electrons, how the electrons are sharing with the hydrogen, we'll see. So whereas each of the hydrogen atom has a single valence electron. So now each hydrogen, so totally you have 4 hydrogen atoms. These 4, because we are taking methane as an example here. So 1 is the carbon and 4 is the hydrogen. So carbon is having 4 valence electrons on the outermost shell, and the hydrogen is having a single valence electron. So 1, 1, 1 and 1. Okay. So here the hydrogen is having 4 hydrogens that are having a single valence electron. So here carbon is having 4 valence electrons and hydrogen is having each one of 4 electrons. So 1 into 4 you have get 4. So each hydrogen has a 1 valence electron. Now how there is a covalency nature between the C and H4, that is the methane, we'll see now. So each hydrogen atom can acquire a helium electron configuration. So how we are getting that hydrogen how we are getting that hydrogen to helium configuration means, here what is happening, the carbon atom shares with it 1 electron. So each carbon atom is sharing with the hydrogen. Okay, since we have here in the outermost shell 1, 2, 3 and 4. So total 4 valence electrons are there on the carbon, and if you see in the hydrogen, you have this is the H, each having only 1. So see the clearly figure here, shared electron from carbon and shared electron from hydrogen. Okay, now both the carbon as well as the hydrogen atoms are sharing. So because of that sharing, what is happening here, we'll see. So the carbon now has 4 additional electrons. So initially only 4 electrons, valence electrons are there. Now because of the sharing from the hydrogen, additionally 4 electrons are being shared to the carbon from each hydrogen atom. So total how many you are getting? So here you get 2 plus 2 plus 2 plus 2. So totally here 2 plus 2 plus 2 plus 2. Total 8. So totally we are getting 8. So carbon has now 4 additional electrons, 1 from each hydrogen. So because of the each hydrogen, from each hydrogen, totally you are getting 8 valence electrons and this is the electron structure of the neon. So this is how you're converting that hydrogen into the 8 valence electron with the help of the sharing of the covalent sharing of the electrons between the carbon as well as the hydrogen atom. So the covalent bond is directional, so it is in the directional nature, and this is between the specific atoms may exist only in the direction between one atom and another that participates in the electron sharing. So sharing is nothing but from the both the ends we have to share. So that's why the covalent bond will get a good bonding energy when it shares between the two atoms. So in this case, the carbon as well as the hydrogen are sharing its electrons from the valence valence electrons from the 4 and 4. You're getting total 8. So it is converting into methane. So this is the best example to explain about the covalent bond with the help of the methane. And if we see another materials which are having a covalent bond, many non-metallic elements like H2, Cl2, F2, as well as the molecules containing dissimilar atoms like methane, H2O, HNO3 and HF are covalently bound. So these are some of the examples where you can find out the covalency in nature. So that's why the bonding energy describes the properties of the material. So the materials which is having a good bonding energy we have to select while preparing any material. Now further, this type of bonding is found in elemental solids such as diamonds, silicon, germanium and other solid compounds which is composed of elements that are located at the right hand side of the periodic table such as gallium niarsenide, indium antimony and silicon carbide. So these are some of the examples where we can find the covalency nature for the metallic as well as non-metallic nature, and also some of the solid elementals such as the carbon, that is the diamond, silicon and germanium, and other compounds which is having in the right hand side of your periodic table. If you see that like gallium, silicon carbide, gallium arsenide. So these are some of the examples where you can find the covalency of the bonding. Now the third type of the primary bonding is the metallic bonding. So metallic bonding is the final primary bonding type which is found in metals and their alloys. So where you can see the metallic bonding. So in the name itself you have the metallic bonding. So where you have metals and its alloys, in that type of things you can get the metallic bonding. So a relative simple mode of has been proposed that very nearly approximate the bonding scheme. So how you'll get the metallic bonding means? So in general, what are the things we are using in daily things like automobile, the bicycle, what we are riding, the cups for tea cups, what we are using. So everything is made up of metals only. So why we are trying to use the metals instead of the wood? Suppose if you consider a kettle, so in that kettle you are using a metal. Again in that kettle you have a heater which is made up of also a metal. Why we are using metals only rather than using a wood or ceramic? Why? Why means these metals are very flexible. These are ductile in nature. These are very flexible. So you can modify into any type of shapes. Because of that, electrons which are there inside the body are easy to distribute to any position, so that you can easily manufacture at different types of shapes or different types of geometry with the help of these metals only. Okay, so that's why we are using most of the household things or most of the things which for what we are using in the daily needs which are made up of metals only. So because of the tendency of the ductile nature of the metals, so we are using the metals, and you can find the metallic bonding in most of the metals as well as the metal alloys. So metallic materials have 1, 2 or most 3 valence electrons. So the materials which is having a metallic type of things which has a 1, it can be 1 or 2 or 3 valence electrons. Okay, it can be 1, 2 or 3. So these valence electrons can share to another to get the bonding between the metals. And with these models, these valence electrons are not bound to any particular atom in the solid, or more or less are free to drift toward the entire. So what is happening here? Because of the arrangement of the atoms inside, so this is the positive, positive and positive, like that. This is the arrangement of the atoms inside the body, and here you have some free space. You have some free space in between. So because of free space only, we are trying to bend the material, or we are trying to manufacture in different shapes. Why? Because of the free shape is there inside in between these positive, and this free shape, free zone is called as an electronic cloud or sea of electrons. So somewhere you will have some positive energy here, negative, 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 like this. So because of the free flow of electrons, so that is called as an electronic cloud. So because of that, you can do any type of geometry with the help of these metals, and these free flow of electrons, which are used to change the shapes, act as a glue. So this will try to bind the positive charges to get it a good geometry. So the remaining non-valence electrons and the atomic nuclei from what we are called as ion cores, which possess a net positive charge equal to the magnitude as well as the total valence electron charge per atom. And if you see the complete picture of the metallic bonding, so now you can get a clear idea. So these are the atoms which are located at positive things. So each atom is a positive charge, and you have some free space. So this free space, what we are seeing in the blue thing, this is called a sea of electrons. So sea of valence electrons. So these valence electrons will share. So these free valence electrons will try to share with the, like this, to get a bonding. So that's why these sea of electrons or sea of valence electrons act like a glue or act like a binding in nature to bind the electrons in the metallic compound. So this is the schematic representation of the metallic bonding in terms of the primary bonding. So the free electrons, what we are seeing in the schematic figure, shields the positive charge ion cores from mutually repulsive electrostatic force which they would whether exert on the another. So what is happening because of the at same charges? What happens if there are same charges side by side? There is a repulsive force, but we should not get the repulsive force. Since it is a bonding, we have to get a different charges. So what we are trying to do, we are adding some negative pole here. So because of this negative, what is happening? It is trying to attract each other. Instead of repulsing, we are trying to attract the molecules inside. So because of that attractive force, we are to bringing there the sea of valence electrons which are present in between the positive charges. They are acting as a glue in the metallic bonding. So that's why the free of electrons acts as a glue to hold the ion cores together. So always this free flow of electrons, though we are using to do in different geometries, the free flow of valence electrons are used for as a glue to get the bonding or the energy between these things. Now if you see the different bonding energies of different materials with respect to the type of bonding, here you have the ionic bonding, covalent bonding and metallic bonding, and here you have different types of substances. You have here sodium chloride, magnesium oxide, silicon, diamond, HgAl, FeNW. So these different types of substances what we have. Now based upon the type of energy in the substance, we have the different types of bonding energy again. So now if you see here the bonding energy of the sodium chloride, you have 640 kilojoules per mole if it is an ionic bonding. So ionic bonding, you have the substances like NaCl, MgO. So if you are choosing any material which is having ionic bonding, suppose if you are taking the sodium chloride example, so it has a 640 kilojoules. This is the bonding energy. So the maximum possible bonding energy what we are achieving is 640. So further we can't get. That means based upon the bonding energy, we can tell that how much time it will take to get a material to a solid state. So from liquid to solid state, how we are converting based upon the attraction between the molecules. Suppose if you have a strong attractive force inside the material, so that you'll get a good bonding energy. So because of that, you can easily tell that how much time it is taking to get a solidification. As well as if you have a repulsive thing, so how much time it is taking to get a liquid state. So all these things we can analyzed based upon this bonding energy and what type of bonding we have. Similarly, if we consider the covalent here type of bonding, we have silicon diamond. Okay, so again you have a diamond is having a good bonding energy because it is having a strong covalency in nature, 713 kilojoules per mole. And if you go with the metallics, aluminum, iron, okay, so it has almost 328, 406 and 8409. So these are the different bonding energies based upon the type of bonding as well as the substances what we are using. So that's why the application is very, very important. Based upon the application only, you will decide the material. And how we are deciding material? Before deciding material, you have to know the type of properties. Again, if you want to know the properties, you have to know the type of bonding energy. So these are all, everything is correlated, interrelated to each other to get a final product. And coming to the second category of the bonding, we have the secondary bonding. So this is also called as a van der Waals bonding energy. So in primary we have three, that is the ionic, covalent and metallic bonding. And coming to the secondary bonding, so we have different types based upon the nature of the bonding here. The secondary bonding is also called as a van der Waals or physical bonds, and these are very, very weak when you compare with the primary bonding. So these are typically ranges in the order of only 10 kilojoules per mole. So this is very, very less amount of bonding energy if you see in the secondary bonding. Why? Because there is a lot of loose attractive force between the atoms. Why? Because the arrangement of the atomic structure is not proper inside the material which is having a secondary type of bonding. That's why we have to select a material which is having a good bonding energy, that is the materials which is having a primary type of bonding things. So we should not go with the secondary type of bondings because it is having very, very less energy. So based upon the application, again, if you have a less bonding energy type of materials or products, if you need to prepare, then you have to go with the secondary type of bonding. So but that's why the application is very, very important in any case. So secondary bonding exists between virtually all atoms or molecules, but its presence may be hidden. Why? Because see, if you consider any type of atoms or molecules, the secondary bonding exists. There is an existing of the secondary bonding. Why? Because somewhere you can find the loose bonding nature. If you find anything in the loose, that means suppose if this is the atomic structure, I have a positive, negative, like this arrangement. Okay, etc., like this. So somewhere, so this is the different energy levels you have, but somewhere here you have both positive. So both positive means there is a repulsive. That means you have an existence of the secondary bonding, though it is a primary bonding, but we are trying to hide them. Why? Because the primary bondings are the presence of primary bonding is more when you compare with the secondary bonding. That's why, because of the presence is very, very high of the primary bondings, the secondary bondings are hidden, though it is being existing. So that's why in any type of materials, we have the existence of the secondary bonding, but because of the presence of the primary bondings, the secondary bonding is being hidden. The secondary bonding is evidence of the inert gases, which is having a stable electron structure, and in addition between the molecules in molecular structures that are covalently bond. The secondary bond forces arises from the atomic or molecular dipoles. So how we are achieving the secondary bonding means with the help of the dipoles. So what is the use of dipoles? So dipoles are used when there is a weak attractive force between the molecules. So these dipole acts as a bridge to connect or to create a bond energy between the atoms. So where we have a less bonding energy, these dipoles have been used. So in essence, an electric dipole exists whenever there is some separation of positive and negative portions of an atom or molecule. So if there is an existing of some separation of a positive and negative charges, we are using these dipoles. So the bonding results from the Coulombic attractive force between the positive and the negative end of the adjacent atoms as indicated in the figure. Now if you see the figure, so these dipoles try to create the bonding between the atoms which is having a very less charges. So if you have a very few weaker positive and negative charge, there is a very less attractive force. Now these dipoles acts as a bridge between these two elements to get an attractive force. That is the importance of your atomic dipoles. So dipole interaction occur between the induced dipoles and polar molecules. So wherever there is a weaker section of the bonding energy, where there is a weak charges of positive as well as negative, where there is a weak or less attractive force between the atoms or the molecules, these dipole interaction is very important. The hydrogen bonding is a special type of secondary bonding, is found to exist between some molecules that have hydrogen as one of the constituents. So though the secondary bonding which is having very less type of bonding energy, the hydrogen is a good example where though it is having a secondary type of bonding, but it is having a covalence nature inside. So because of that covalence nature already present inside the hydrogen atom, so this will act as a good attractive force, and if you combine this hydrogen with other secondary type of elements, then it is very easy for us to do the bonding between the elements with the help of the hydrogen atom. So that's why hydrogen we are using with the other secondary type of bonding materials to get a good bonding energy between the materials. Now we have another type of things in the secondary type, fluctuating induced dipole bond. So fluctuating, so in the name itself it is showing it's fluctuating. So during the sharing of electrons, so what is happening? Continuously it is rotating. So because of this rotation, continuous rotation, there is some vibration. So because of this vibration, what is happening? There is a change in the orientation of the atom or the molecule. So because of this change or drift in the atom or the molecule, what is happening? The positive and negative charge may get diverted. So because of this diversion, what is happening? There is a existing of the same poles coming into picture. So because of the same poles are coming into picture, there is a repulsive force. There is a not strong correlation or strong bonding between them. So generally what is happening? There is a good bonding. There exists a good bonding when there is a symmetrical nature. If you see the figure A, here the electrons are exactly symmetric to the nuclei. So because of the symmetric in nature, what is happening? There is a strong correlation, strong bonding between them. So positive, negative, positive, negative, positive, negative, like this. You have a good bonding because it is having a symmetrical shape. Now, slowly this process, what is happening because of the sharing of electrons, because of that constant vibration motion is existing, what is happening? This symmetrical is changing to unsymmetrical shape. If you see the figure B, so what is happening? The shape is changing to a different shape, unsymmetrical shape. So the position of this atom is changing from the center to somewhere nearer here. It is coming very close. So what is happening? Initially the position is at this point, now it is changing to this point. So what is happening? Because of the change, some another atom is coming into picture here. Maybe this is positive and this is positive. So what happens? Both positive, again there is a repulsive force. So that's why we are using these dipoles. So we are using a dipole which is having a negative and positive. So because of this, there is a attractive force. So that is a bonding energy. So this is how we are adding some dipoles to get the bonding energy, to increase the bonding energy. So that's why always, because there is a change in the orientation of the unsymmetrical nature, there is a less bonding energy in case of this secondary type of bonding. So this is another type of secondary bonding, that is the fluctuating induced dipole. So though it is being fluctuating because of that continuous vibration, we are using these dipoles. We are trying to induce the dipoles inside to get a strong energy between the atoms. One of these dipoles can in turn produce the displacement of the electron distribution of an adjacent molecule or atom, which induces the second one also to become a dipole. So then we are getting a weak attractive bond to the first type of bonding, and this type of bonding is called as a van der Waals bonding. So because of the unsymmetrical nature, what is happening, the position of this electron is changing from one position to another position. So initially it was somewhere here positive. Now because of that orientation or the unsymmetry, this position is slowly changing to this position. So now this position is getting empty. So because of this position is getting empty, some another atom is trying to replace at this point. So now what is happening? Nearby again you have some positive, negative. So because of this, there is a repulsive force. So again, since we have a repulsive force, here you are using a dipole to get an attractive force between. So like that you are trying to add some, you are inducing some dipoles to get a force of attraction between the atoms or the molecules in case of the secondary type of bonding. And the liquefaction, in some cases, the solidification of the inert gases and other electrical neutral symmetric molecules such as H2Cl2 are realized because of this bonding. So the materials which are having H2Cl2, though they are having some good bonding in nature, because of the liquefaction or solidification of these elements of these molecules, what is happening? We are getting a very less strength, very less bonding energy. So because of that nature of the secondary bonding, we are trying to realize what type of bonding or what type of atomic structure we have in terms of H2 and Cl2. So because of this type of bonding only, we are trying to characterize, we are trying to bring out what type of characteristics the H2 as well as the Cl2 metals are having based upon the type of bonding. In the similar way, the melting and boiling temperatures are extremely low in materials from which induced dipole bonding predominates, and all possible intermolecular bonds, these are the weakest. So completely these are very weak. Why? Because we are trying to induce some dipoles to get a bonding energy, and these dipoles are also very used where you have a less energy levels, less weak energy, less energy is there we are trying to use. So because of that, again the energy is also dropping. So if we don't have a good bonding when you compare with the metallic or ionic or covalent bond, so because of that we are inducing some dipoles so that you'll get a less energy when you compare with the primary bondings. So that is about the induced fluctuating induced dipole. The third one of secondary bonding is the polar molecule induced dipole bonds. So in this case, what is happening here? The permanent dipole moment exists in some molecules by virtue of asymmetrical arrangement of positive and negative. So here it is asymmetric in nature. You're not having a same shapes of the two atoms when you compare here H and Cl. It is unsymmetry. Why it is unsymmetry? If you see in this figure, you have a different symmetrical nature. You have small size and bigger size. So this is an example of the polar induced dipole. So this exists in some molecules by virtue of asymmetrical arrangements of positive and negative charges. Such as molecules are termed as polar molecules. Okay. So what is happening here? Below figure is a schematic representation of the hydrogen chloride molecule, a permanent dipole moment which arises from the net positive and net negative charges that are respectively associated with the hydrogen as well as the chlorine ends of the HCl molecule. So here you have a two hydrogen and chlorine molecule which is unsymmetry, and here also you have another, if you consider hydrogen Cl. Now what is happening? Here both the hydrogen atoms have the same charges. So here we are trying to induce a dipole to get a bonding energy. Though it is not similar to your fluctuating. Why? Because it is fluctuating its position from one position to other. Because of the fluctuation, you are getting a less energy, bonding energy. But when compared with the polar molecules, you have a good bonding energy with the fluctuating polar molecule. So here polar molecule can also induce dipole in adjacent non-polar molecules, and we can get a good bonding attractive force because of this induced dipole between these two molecules. And again, if you find out the magnitude of this type of bonding, you will get a greater energy than the fluctuating induced dipole. So this is the difference of the bonding energies between the uh, primary as well as the secondary bonding. So always you have to select a material which is having a good bonding energy based upon the type of bonding we have. Though it is a some materials will have a covalence in nature, but in some cases the materials which is having a fluctuating dipoles or polar molecular dipoles, we have to identify how we have to differentiate these two based upon the how the atoms are being changing, how the bonding energies are there. Based upon that, you have to select a good material. And coming to the another thing, permanent dipole bonds, van der Waals forces are also exist between the adjacent polar molecules, and these associating bonding energies are significantly greater than the bonds involved in the induced dipoles. Again, these type of bonding energies will have a good values of bonding energy when you compare with the induced dipoles. We are not inducing any dipoles here. So since we are not inducing any dipoles in this case of permanent dipole bonds, we'll get a good bonding energy when you compare with any type of induced dipoles. And the strongest secondary bonding type, the hydrogen bond, is a special case of a polar molecular bonding. It occurs between the molecules in which the hydrogen is a covalently bond to fluorine, oxygen as well as nitrogen. Though we have some secondary type of molecules which is having a less weak in the bonding energy, we are trying to add the hydrogen. We are trying to add the hydrogen since it is having a covalency in nature. So because of that covalency in nature, we are trying to add this hydrogen to other molecules to get a strong bonding energy. So that's why the hydrogen is added to the fluorine, oxygen and nitrogen to get a strong energy, though it is a secondary type of bonding. So that's why we can increase the bonding energy, though it is a secondary bonding, with the help of some other atoms which is having a primary bonding. So since in this case the hydrogen has an covalency in nature, that is the primary type of bonding is there in the hydrogen, we are trying to collaborate with the hydrogen to the fluorine, oxygen as well as nitrogen to get a good strong bond between them. So for each hydrogen, if hydrogen fluorine, hydrogen oxide and HN bond, the singular hydrogen electron is shared with the other atom. So the valence electron of each hydrogen is sharing with the fluorine, oxygen as well as the nitrogen to get a good strong correlation between them to get a good bonding when you compare with the secondary bonding. So like this it is being sharing the hydrogen. So both are sharing with each other so that you will get a strong bond when you compare with the other type of bondings. And permanent dipole bonds are the thing what we have here. The hydrogen end of the bond is essentially a positive charge bond where it is unscreened by electrons. So what is happening here? So though we have a less shape here, less type of hydrogen, what is happening? It is unscreened. You can't see this. You can see generally both fluorine atoms are looking side by side. Okay, since the hydrogen is very small here. But though it is having a positive, we can't see, it is unscreened by some electrons in between. So what is happening? This highly positive charge is trying to attract with the fluorine atom so that you will get a strong bonding energy between these two and you will get a good bonding energy. So this is what is happening. So though it is unscreened because of the other electrons are coming into picture, this hydrogen has a highly positive charge end, and this is capable of strong attractive force between them, between the negative and the adjacent molecules to get a good bonding energy. So this is the single portion of electrons which is acting as a bridge between these two. So between these two, it is acting as a bridge. Though you can't see, but there is a existence of the hydrogen with a positive charge so that you will get a strong bond between these two. So this is a very high energy when you compare with any type of other secondary type of bonding. We are getting almost 51 kilojoules per mole. So this is a good bonding energy if the hydrogen atom is involved in the secondary type of molecule. So this is the importance of the hydrogen, where the bonding energy can be existing. Now, if you compare overallly the different bonding energies of these are the primary bondings, and these are the secondary. So if you see, you have very less energy. So these are all the primary bonding energies, and you have very less. But once if you add with the hydrogen, you are getting a good values of 35 and H51. So these are good values when you are adding the hydrogen with other secondary type of molecule. So this is the importance of the hydrogen. Since it is already existing a covalence in nature, it is trying to get a good attractive force to the other type of secondary substances. And you can get the these are some of the references books where you can get the information about the type of bondings, what are the classifications of bonding, what are the different types of bonding energies are available, what is the impact of the bonding energy in each type of material, and how the properties are being varying with the help of the atomic structure, and what is the importance of selection of material based upon the type of bonding. So all the different types of bondings, everything we can find out from the some of the references books. So first one is the Introduction to Physical Metallurgy by Sidney Hebner, and the second is the Essential of Material Science Engineering by Donald, and the third one is the Material Science and Metallurgy by Kodigiri, and the fourth one is Material Science and Engineering by William Kastler. So these are the four references books where you can get the information about all the bonding energies, different types of primary as well as the secondary bondings, what is classification and subclassification, and what is the importance of these bonding energy, why we need to study the bonding energy, and what is the importance of this bonding energy and how it is impacting the properties of the material. Everything we can learn from this session. Thank you for listening.
Like, share and subscribe. Hit the bell icon for more updates.